Rahim and Assalamualaikum and good afternoon to everyone. So I think first of all, I would like to say thank you to our prominent speaker, Prof. Brent, to be here with us. And to everybody who joined us today, thank you very much. So definitely we are excited to have you all here and take this opportunity to learn from our guest speaker. And my name is Zainal. I'm academician in University of Malaysia as a process control professor in that School of Chemical Engineering. So I'll be your moderator for today. So before we start, I would like to introduce our guest speaker. Professor Brent Yang is a professor and chair of food and process system engineering at the University of Auckland, New Zealand. Thank you very much for to be with you today. And he holds a PE in 1986 and a PhD in 1993 in chemical and process engineering from the University of Canterbury, New Zealand, and has experience as academic and consulting engineer in Australia, Canada, and New Zealand in process control and design, which is really much related to my PCS. And he has been a chair in the Department of Chemical and Material Engineering at the University of Auckland, New Zealand in 2011, where he has been the director of the Industry Information Economics Center from 2007. His specific research and engineering experience is in developing digital models, which is very good, shadow and twin for food and process systems. And he also teaches a fellow of both of the IKB, United Kingdoms, and New Zealand. He was the recipient of the 2014 Australasian Award of Excellence in Chemical Engineering in Teaching. And for your information, the program has published more than 200 refereed publications, patents, and also a co-author of 2 novel teaching texts on process control entitled of A Real-Time Approach to Process Control and Control of Aluminium Production and Other Process Industries. And another textbook is coming, co-authored by him in 2023 with the title of A Real-Time Approach to Distillation Process Control. I think everybody are looking forward to this book, Prof, A Real-Time Approach to Distillation Process Control, which is very common to chemical engineers. So again, without further ado, I would like to welcome Prof. Brent for your presentations. And the floor is yours, Prof.
Thank you very much, Prof. Zainal. Appreciate the introduction. Just give me a moment while I sort my screen out and share my presentation. So make sure that we've got it. Just want to make sure that you can see my PowerPoint. Actually, if I go to full presentation, can you see the full screen presentation? Yeah, let's see, I see a thumbs up, so that's great. So today I'm going to talk about digital twins and process control and our work in this area. Don't be fooled by the blue sky background. A lot of this is not blue sky. A lot of it's actually quite applied. That's just our stock standard University of Auckland PowerPoint slides. I quite like it, but you'll see. Anyway, you can be the judge of whether it's blue sky or applied. Right. So what we're going to cover today is I'm going to talk a bit about digital twins and what they are in terms of process control, and then talk about tool development. I'll present a whole site optimization study and also an example of hybrid process modeling, a tool that we're developing, and round out with some current and future research in smart energy systems. I ought to add that in some ways the process control here is being used in the broad sense. So we're going to be talking a lot about, I guess, process optimization, which will encompass process control, but also optimization of a process, a plant, and even a whole site, and even beyond into into the community and the grid, for example. And again, more on that later. So first up, digital twins. What are digital twins, I hear you ask? Or maybe not. You probably all know what they are, perhaps I should be asking you. You may this curve here is the is from Gartner. It's the hype curve for emerging technologies, and there's a lot of hype about digital twins. I don't actually explicitly see digital twins on this curve, although I see digital humans. However, it's possible that that we are actually very much on the hype curve with that term. I'll deal with this shortly in a minute. The way that we are dealing with the fact that we are working in digital twins is that we're not just creating new technology for the hell of it. We are also looking at solving problems, applying it to real engineering systems. And I think that's when where you can get through this hype curve and get to that plateau of productivity, which is where the hype of a new technology is over and actually becomes practical. What is a digital twin? So this is our definition. A digital twin is twinned with a physical asset. So in our case, being process control, typically is a process plant. And that digital representation looks like, behaves like, and connects to that system. And the idea is to, we want to optimize, or control if you prefer, decision making across all time horizons. And this could be from the classical PID control, so that's or into more advanced controls such as MPC, model predictive control. But as I've hinted at, this could go into optimization, scheduling, and even at activities such as retrofit and process design. So again, I'm using process control to almost encompass all of these sorts of activities which are within the realm of process systems engineering. So another way of looking at this, previous authors, Kritzinger a few years ago had a definition which we quite liked, and we've kind of borrowed from it and hopefully improved on it. But the idea of where our digital twin fits with respect to digital models, and you've got your industrial plant, you've got a model which you might get out of a textbook. That is the classical situation, and the two are not connected. When you have a model, you could connect that to the plant either offline by validating that model with respect to the various parameters, or you could you'd have a more continuous connection to the real process plant, and that is termed a digital shadow. In this case, there's automatic data flow going from the plant to the digital shadow in this case. The digital twin is where you got that two-way connectiveness, the two-way connections, the automatic data flow between the two. We also have other data flowing in from which are product and process requirements that we are setting on that digital twin and that industrial plant. So we actually, in some ways, we think we like to see these three different types of situations as forms of digital twins. So quite often we use the term digital manager to refer to the high level digital twin here. If you want to know more about some of this classification, we've published a recent paper with respect to energy digital twins, because it's where we are applying a lot of our work on digital twins, as you'll see later. More on that definition. I've mentioned about the connectiveness. I haven't talked about the sort of the looks like and behaves like fidelity aspects. And I've drawn up a figure here which sort of shows you the looks like versus behaves like fidelity. So we've got 1, 2, or 3D representations of our plant. So 1D, the low level, looks like fidelity might be a block flow diagram, whereas a high fidelity looks like fidelity might be a transient CFD model. Similarly, that behaves like you can go from single steady state to multiple steady states to dynamics, and use of the digital twin in any of these sort of use cases, and therefore the fidelity of the digital twin is going to change. If we think about this as we go, because we're getting more complex, I guess, and higher fidelity as you go from left to right, from the left bottom corner to the right top corner, you've got better decisions, hopefully, if you've got better, more accurate models. However, because you're capturing more of the physics and so on. However, you need to run these models. So, for example, a transient CFD may not be particularly practical if you're trying to solve a steady state problem on a process plant. So you might need some real serious computing power, some quantum computing for that to be feasible. So as you go down that diagram from the top right to the bottom left, you've got fewer resources required to build your digital twin. So that's something to bear in mind when we're thinking about our digital twin, and it's sort of horses for courses. The model should fit the purpose for what it's designed for. How will digital twins help? So we're going to talk about this in some more detail coming up, but particularly we're focusing at the University of Auckland on real-time optimization and control of processes, but also beyond, as we mentioned. We are looking at things in asset management, so retrofitting, replacing and retiring equipment, but also particularly focusing on energy and such things as decarbonisation. And we've actually looking at applying digital twins of industrial heat pumps to help New Zealand with its decarbonisation of its process heat, which is, I guess, a common challenge globally as we're all working towards sort of zero carbon by 2050 or sooner, in fact. So here's a sort of showing how digital twins might relate to the improvement cycle. Here we've got on the inside, the yellow circle is a operational optimization cycle. And on the outside, we've got the asset optimization cycle. And here we might have that automated R-cubed analysis that I talked about just before. It's the retrofit, design or retire, making decisions using digital twins to help us make decisions in that area. Might be looking at technology options and modeling that and looking at the costs, again, at that high level. Or we could be getting inside these circles and actually looking at operational digital twins, and as well as these engineering design digital twins. And so this is the space that we are playing in with digital twins. Just about most of the important spaces, if you think about it, in process systems engineering. So what's needed? Our hypothesis or our argument is the fact that tool development is actually needed. Now, often people will try and sell you a process simulator as a digital twin. And that really is just an example of rebranding. We believe for these digital twins to be useful, to really apply and give that promise of delivery, we need to exploit Industry 4.0, the Internet of Things, big data, and what we know about machine learning. And then we need to look at these different digital twins of different fidelity and integrate them so they can work together in harmony. So you might be looking at a factory or plant digital twin. How does that integrate with, say, a digital twin of the electricity network, for example? So, tool development, I think, is very necessary to really achieve on that promise of digital twin. What we are working on in the centre that I'm part of, which you'll hear about, is we're working on using an open source platform. Currently, we're using DW Sim process simulator, but that kind of doesn't matter. It's the philosophy of open source. As we are applying this particularly to the question of process heat and decarbonisation, we're looking at the sorts of tools that are shown on the right here. So we are looking at process simulation, but smart process simulation that can build fit for purpose digital twins. We're particularly interested in process electrification because that's how we're going to decarbonise, and also at the design retrofit level, we're particularly interested in process integration tools. So we've got to develop digital twins that can do the likes of surrogate modelling. Think about the likeness of the system, include data analytics, and think about how we might switch resources in our process plants, such as different fuels and different energy sources, and not forgetting how it actually integrates with the entire community, particularly if we're looking at decarbonisation type applications. So just in some more detail, what we're looking at in particular on those sort of three different tool sets. So pinch analysis, bridge analysis, and spatial analysis tools for process integration. We're looking at how we build and include heat pumps, for integrated process electrification. And we'll be doing this both at steady state, but also dynamic modeling. We need that level of fidelity. As part of this, we'll be doing 3D scanning of plants, so we can, because I think one of the aspects that's really important, that's going to be important, is that likeness attribute for digital twins. And so we're going to be applying this with, we can look at real process plants, but at the moment we're actually looking at real process plants in one of our university laboratories. Now I might have to stop sharing and share another screen here, because this, for some reason, I might have to cut over to the actual to a different video feed. So if I just bear with me while I do that. So I'll share, and if I got the right one, hopefully you'll be able to see this. If I start playing this video, these videos, what we're looking at, actually I need to probably do one at a time. What we're looking at is, a real plant at one of our university laboratories, which we've actually done some 3D scanning on. So a couple of students that are up here in the picture who are actually doing this work. And the idea is to explore this for ourselves, what we can do in terms of 3D scanning. So you can get quite detailed information, if I can just get this right so that it moves. I'm hoping that it shows for you. You can see here I'm hoping that that as we walk through virtually, we can actually use the 3D scan to walk through and get perspectives on equipment and its operation that you wouldn't be able to get from from any other way, vantage points. So we can use this, actually enhanced 3D likeness aspect to really add value to understanding of the digital twin. This is still very much in, you can also get very accurate dimensioning of this with point clouds, point clicks, and so forth. This is something that we believe is going to be very important, or this is very much in its infancy at the moment for us. Okay, I'm just going to stop that sharing, if I can. sorry. Stop sharing and then cut back to my presentation. Sorry about this. Where are we? Screen. I think I'm sharing the wrong screen. Oh no, okay, so hopefully you can see a screen that says virtual and augmented reality. And where, in fact, we can see people with headsets looking at heads-up displays that are just completely virtual. This is not me. The person in the headgear on the left is my colleague, Dr. Martin Atkins, who's been pioneering the work for us at our centre. So before we get into that, I'll step back and look at some of the sort of things that industry wants us to look at and where we think digital twins might be applied, because this is a bit of a journey. This is a real whole site optimization study conducted for Fonterra, which is New Zealand's biggest company. Fonterra has several thousand employees and is responsible for something like a third of New Zealand's export earnings. So it's, in some ways, I think the only like globally is Petronas in Malaysia. It's a big company that dominates the economy of our country. We were tasked with looking at optimizing and scheduling for a particular site for Fonterra that had lots of different dairy processing plants. So they received milk from local farms, and they also received cream, and then they process it to produce whey, skim milk, ultra filtered milk, and also extract milk minerals. This is quite a complex operations. It's mainly, this process is actually mainly tanks and switching. As you can, there's a bit of heat transfer, refrigeration and so forth, but there's a additional wrinkle that there's cleaning required, so you don't grow biological cultures in your milk. People usually get very upset when that happens, unless it's obvious for obviously required for something like yogurt. So at the moment, it's perhaps no surprise to you that the way that the schedule and the optimization is done by the planners is it's done manually with an Excel spreadsheet. With this complex operation, there's lots of opportunities to get a far better optimized process that could be efficient and save energy and optimize the production of product. However, what they also want is, the client that is in this case, is that they want a flexible scale solution. At the moment, they find that their Excel spreadsheet is not, while it's good for what they've got, it's very difficult for it to go and scale to another process or another plant. They pretty much have to start from scratch, and it's very difficult to really troubleshoot. So what we were doing is basically building a basic simulator. I've been guilty of what I've accused other people of doing and saying that we are building a digital twin. In this case, we are actually building a digital model, but with the aim of it becoming a digital twin in the future. We're using this to check the plausibility of solutions that the planners could come up with. And currently, they don't do that. They just do their planning and see what happens, and then use this as an input to developing an optimization. So that we can formulate constraints, so we can make sure they're in an appropriate form and therefore solved by our optimization solvers. And ultimately, we want to solve this by to create an optimal schedule for the client using something like a linear program solver. So the overall schematic of the optimization kind of looks like this. We've got disturbance variables and mainly the inputs to the process, the milk and the cream coming at various times of the day. We want to manage the production levels and the tank levels. And how do we control that? We can decide whether turning on a valve or off, turning a valve off should be done. We want to avoid overflows of tanks or other exceptions, and we're using the optimizer to solve this problem. So the initial strategy actually was to apply this to using their Excel spreadsheet. And actually it was used by the plant managers. It did work quite well, but it didn't get it still didn't solve the problem of scalability. Also, you didn't get a sort of a WYSIWYG or even any sort of GUI with it. So at least as a first pass, and we built a crude process flow diagram using MATLAB and Simulink, which is amazing because normally industries run a mile from MATLAB. But in this case, we convinced them that actually it was a useful solution for them. And it was a very good conversation starter with the company because we could sort of diagrammatically show them the process operation, and that's sort of really what the managers understood more than pouring through a spreadsheet. Here's the full plant P&ID and Simulink. Okay, it's quite zoomed out and it's a bit hard to read, but digitally, no problem. You can zoom in and have a look at what's happening. You can look at what is happening in real time. You can see where there's overflows or exceptions and so on. So very easy to do. This is, I guess this is really current technology. Nothing researchy about it, but it demonstrates the utility of visual twins to the managers in this case. There's such things as constraint checking. Here, looking at in real time, looking at whether there is a problem or not. With this, we very quickly developed a PFD which the users were actually found they could use, even though it wasn't perfect, perfectly rendered HMI. Plant was rather simple from a process systems point of view. It's pretty much a separator and lots and lots of tanks with their dynamics of the tanks described by their volumes and piping connecting them, so time lags there. So we actually currently have 3 implementations, and you've seen the graphical side shown with the Simulink. We want a more beautiful PFD and perhaps a higher fidelity PFD. Then we might need to look at commercial process simulators such as HYSYS, or the approach that we're taking before is looking at open source simulators, and DWSIN is one example. And we're going to be doing that for the client to see where that leads us. So back on track, developing tools that can manage the data in these sort of systems. One thing about these, when you get into modeling and control of process plants, is that that you find that you have parts of the plant that you can model mechanistically, and parts of the plant we have lots of data, but you have no. And so that's where the idea of hybrid process modeling comes into play. And I'm going to describe some research that we've been doing for the last 18 months or so, and developing a tool that can aid in developing good hybrid models. Just as definition of what I mean by hybrid models, that it's a formal combination of mechanistic models with data-driven type models. So your mechanistic model might be something like it's an equation, a fundamental physical representation of the physics, whereas the data-driven model might be something like a gain model or an artificial neural network, and fusing them together it gives you a hybrid model. Arguably, simulators like ISIS, you could say, are actually, in a sense, hybrid models, because they have parts which are data-driven, purely regressions, and they have parts which are related to the physical understanding, a physical mechanistic model. So when it comes to looking at process data, often the assertion is that big data means good data. And I hope I will disabuse you of that notion if you believe that. I'm sure you don't. But the idea, quite often, the idea is that if we just throw sensors at a plant, and if we make lots of measurements, get lots of data, or maybe we've got years of data from an old plant, it's going to tell us something about that we don't know about the process. Unfortunately, that's very often not the case. The reason is that the data often is poorly excited, and that means you're often controlling around a single set point, and so the data exists in a narrow band. And so in the figure here, you see that there's a correlation here between condenser pressure and air temperature, and it ranges over obviously the air temperature will range, but you see the condenser pressure doesn't change that much, and it changes over a relatively narrow band. There's few data points in the top left quadrant of the figure, and few data points in the top bottom right quadrant of the figure. You can see the probability density distributions of the data points indicated at the top and right-hand side of the figure. This we would call a relatively imbalanced data set, and that's true of most industrial data. It's really centered on those common operating points. You don't have much data outside that. Now, for good reason. It might be uneconomic to operate at high pressure in this case, and so you actually want to avoid that. You also perhaps don't want to go to high temperature, because that could be an unsafe area of operation. And so these limits, constraints do exist, and it's good process control to be aware of them and control to them. But if you really want to understand how the plant is going to behave and when it fails or when it gets close to a failure case, you need to take a look at this fact that your data is imbalanced, and we need to rebalance that data so that the outliers have some weight. And so our models can reflect when we are heading towards the uneconomic region or the unsafe region. So in literature, there's been several techniques that have been employed to use this. You could just go out and make more measurements if they're available. Often that's not available in a real process plant. It costs. There's another technique called cost-sensitive learning, which includes that idea. Or there's another technique which involves undersampling. So if you look at the common mode measurements, you'd undersample those, and you might oversample the edges, the data that are the extremes. And so we're going to particularly look at a technique that involves oversampling. I should say that SMOTE, this is the figure on here, is the current state of the art for technology. It's for this tool and technology. It's not designed for process data per se, and it comes from application in bioinformatics. So we developed this new technique called classless oversampling technique, or COVERT. We had to have a nice acronym. And the idea is to have that generates synthetic data that fills in the data, and so you can get that get information on those rare points, those exciting points. So we get a more uniform distribution. The idea is to identify those exciting regions, not go unsafe, but generate synthetic data in those regions. So this is an example, or it shows you a simulation of the technique where the blue represents the original data set and the orange represents the filling in using the covert technique. And this is just a dummy example of some XY data with a particular probability density distribution. Actually here I've just updated it, and you can see the orange data filled in is the filling in of the fringe areas with making a more uniform distribution, as you can see indicated on the sides of the figure. So we've gone from this to this. We also, that was all well and fine with a toy data set, but we applied this to a real data set. In addition to working with the food industry in New Zealand, we're also working with the geothermal power industry, and we applied this to a real geothermal plant that is shown here. And this plant could be well modeled by the use of 9 input variables and 4 output variables. I won't bore you with those details. Essentially, we had a very reliable steady state with a model with uncertainties expressed, and we decided to do a comparison between our algorithm and HYSYS model of this plant, which we saw as representing perhaps the ground truth of what the data could show. So here again, here we see steam flow rate versus air temperature. They're just picking out 2 variables, and this is so we can show it in 2D space, but of course actually this whole thing works in 13D space because of the 13 different variables. You can see it filling in the data points with the synthetic data points to give you that uniform distribution. I mentioned before that SMOTE was the state-of-the-art tool that's used. You can see its performance on the right versus ours. They initially looks very similar, but we end up with a more uniform distribution, whereas the SMOTE technique tends to be a bit more peaky. And if you compare it to other examples in the literature, we can see here that ours, which is the solid line, outperforms based on several different criteria: the Kolmogorov-Smirnov test, the chi-squared test, and also based on integrated absolute error. We also, as I mentioned before, we wanted to compare it to HYSYS, and it's a bit hard to see here, but we've got in the red, we've got the original data set. The blue is the validated HYSYS model of the ground truth, if you like, and our covert is in green, and the SMOTE technique is in orange. And you can see here, arguably, that covert sort of sits somewhere between the original data set and the HYSYS model, whereas actually SMOTE is actually slightly outside both. It's a bit easier to see if we sort of rotate it in 3D space. The points here are sort of the data that were used for the model. Again, the actual whole data set would be in 13-dimensional space. This work, I should say, has been part of the next part of the talk, which is on Ahuroa Smart Energy Systems. It's a Centre for Smart Energy Systems in New Zealand, and the work was performed by Isaac Severinsen, who's in the picture here. He's the one wearing the lanyard not me. So he's the second one wearing the lanyard. Isaac, for his sins, is doing a PhD with me currently. So what is the Ahu'ora Process Energy Systems Centre doing? Well, it's perhaps no surprise to you, I've given the game away already, that we're working on process heat decarbonisation for New Zealand. So we've got this whole research program for doing this, and we've particularly got these aims. We want to improve plant efficiency. We're going to use boilers and heat pumps to do that, and renewable energy. But the key thing in terms of technology is that we're going to be using adaptive digital twins for smart design and operation. And so one of the tools that I mentioned just now, that Covert tool, is one of these smart design tools that we're developing to assist with that. The centre itself, Ahu'ora, which is a Maori name, our local indigenous population, the local tribe gifted the name Ahu'ora to the Centre for Smart Energy Systems. It's quite a large undertaking. You can see here the numbers. It involves 3 universities, and because we've got our large industry partner, we can actually rightfully say we've got over 50% of New Zealand's process industry behind the centre. And I'm advertising to you, we are, if you want to do a PhD, we do have scholarships available. The numbers here are current numbers, but we've got at least another 10 PhD scholarships that we can offer over the next 5 years. So it's a really exciting program that we're involved with. And with the idea of doing that, smart energy systems for decarbonisation of New Zealand processing. Just to give you some technical flavour for what those PhD students are doing, I'm involved with the supervision of 4 of those PhD students, for the 11 that are 12 that are working at the moment. So we have a PhD student who's working on particularly process control of heat pumps, so non-continuous and vapor compression processes. So, and this is something that hasn't received a lot of attention in the literature or even in industry. Industry doesn't quite know how to control these systems, and so there's lots of things we can do in this area. There's elements of the fact that the constraint or the challenge is that a lot of these processes that we're looking at are non-continuous on the demand side, and yet we have to reliably run our integrated vapor compression heat pump cycles on the supply side to optimize the process, but also save energy. And so this is a major challenge. So I have a PhD student who's looking at this currently. We also have at the largest, so that's right at the plant scale. At the largest scale, we are looking at energy flexibility. So this is actually both at the site scale, but also beyond, at the linking to the grid and to the community. And so the yellow boxes here are different energy sources that are available to us, and we're looking at how do we optimize production, throughput and scheduling while optimizing the energy mix. So we're looking at co-optimization. We're particularly going to be using simulation type studies in the optimization sense here to develop tools here that can be used by industry. We also, New Zealand's electricity grid is really quite interesting as well. We've got a long, thin electricity grid, which is 80% renewable, which is very good. But at the moment, there's a kind of a bias by the users that they think that if we put in green energy at one end, we're going to get at the bottom of the long, thin network that we're going to get, that are supplied to the users at the top end of the grid. Unfortunately, it doesn't tend to work that way, and so a missionality related to where you are on the grid is really, really important. So we have a student who's developing a carbon emission tracing model for industry and for the community. And last but not least, we have a student who's looking into process safety. Our thesis here is that, with these way more integrated systems, where you're integrating and controlling very tightly both the supply side as well as the demand side, that and with use of much more process integration, you're going to have problems or challenges with protection, with control, perhaps, but even with design, and particularly with industry who are naturally risk averse of new technologies. And so the idea here is that we're going to integrate safety into what we do. So I have a PhD student here, Lily Pung, specifically looking at the sort of safety enhancement, both from a design perspective, but also from an operations perspective. So I think I'm just about talked out. But I'm welcome. I welcome questions. But I hope I've sort of said what it says on the tin. I've talked about digital twins and process control from the broader perspective. I would like to particularly highlight the likeness and behavior aspects being important in digital twins, and also connectedness, and that probably still needs work on for us. Development of digital twin tools is really going to be essential for this technology to actually blossom and get over that hype curve. I presented a whole site process optimization case study, which is really a beginning of work that we are started on this journey, and then looked at a new tool that we've also developed. And finally, the Smart Energy Systems Centre, Ahuora, where I showcased a couple of projects that we're doing at the moment here. I'd like to acknowledge my co-workers. This wasn't work that was all done by me. It was collaboratively with these people here, and with the support of the New Zealand government for funding, and also Fonterra for the work on the whole site optimization. And before I finally sign off, I would love to be in person delivering this this talk to you, and I'm sure, and we would love to see you over in New Zealand. We've got a couple of conferences coming up, and now that the world's sort of opening up, I invite you down to Auckland next year in October. We are hosting the Australasian Chemical Engineering Conference at Chemica 2023, and I'm on the committee. I'd love to hear from you. If you're interested, please get in touch. Similarly, I'm also a co-chair of the American Institute of Chemical Engineers ICOSI conference that's been held the following year, at the end of the year in December, also in Auckland. And if you're interested in sustainability, science and engineering, that would be a great conference to attend. I know that Malaysia's already hosted an ICOSI before, so hope to see a few of you down to New Zealand for it. October and December are great times of the year to come and visit. October's our spring, December we're into our summer, so I welcome you down. So thank you very much for that, Prof. Zainul. If there's any questions or comments that people would want to make, I'm happy to take them.
All right. Thank you, Prof. Brian, thank you very much for your presentation. It's been very, realize that 1 hour gone by, very, very short kind of times. So I open to questions, Q&A. If the participants have questions to be asked to Prof. Brands, you're most welcome to ask, or you can write in the chat book if you want to, chat box, so I can forward that to Prof. Brand as well. Any questions, guys? from the participants?
Should I stop sharing my screen?
Yes, you can, Prof.
Yeah, that's probably possibly. Then I can also see the
So-
questions too.
Yep. Maybe I have one question to you, Prof, as a starter, because you mentioned about the optimization and everything. You know, one of the biggest problem optimization is, you know, the times to optimize and the converging of the optimization. So in your case, you're facing that kind of problem because, you know, I believe you're aware about like when we apply the model-based control, like model predictive, you know, the optimization routine, something can be very challenging, you know, because the time, the process time sometimes can be very fast, and the converging of the optimization sometimes takes slightly longer than the sample time. So do you facing that kind of problem in your real case study?
Yeah, so with the case study, I guess we were doing, when I said optimization, perhaps it was more scheduling. So we were looking at, so that, yes, we did incorporate the key dynamics, but we were looking at scheduling for a day's operation. So the time, you know, we would run you would probably not run the model in real time. You'd run it as, it would essentially be a multi-steady state model. You could run it in real time, linked to the process, but at least at this stage, we're looking actually replacing the current spreadsheet tool with this better optimizer. But you're right. I think if you want to actually close the loop in terms of closed loop operation, real-time optimization, that is a challenge, no question.
Yeah.
It's not one that we've solved yet. We haven't gone. So I guess in this case, we deliberately decided not to do that. We want to sort of get our feet wet first with the scheduling problem. And similarly with the energy optimization, we'll be looking at, I guess, running in simulation mode. So probably the sort of digital twins that we'll develop, I think, in this area would be more of the form of a digital shadow in some ways, rather than a full digital twin manager, in using the definitions that I mentioned before.
I think you also mentioned about the GUI in your presentation, like, Prof, and you mentioned about the commercial tools like Aspen's, HiSys, and everything. And now people also talking about the dashboard,
Yes.
Dashboard as a tool. So what are your opinion about that? The dashboard, instead of, it's part of the GUI, right? But dashboard, it could be slightly different and slightly easy to develop. Like even Excel have a dashboard tool, you know. What do you think about that?
I think actually we don't want just one tool. I think we want a toolkit, really. And I think dashboards can be part of it for sure. Similarly, so can HiSys and so can the big simulators, but they don't solve every problem. And what we're seeing in industry is that we're seeing people far more, I was going to say the opposite of reluctant, far more liable to take up and apply open source tools using things like Python or even something simple like R to actually code a very simple tool that they can use in their operations. We're seeing far more interest by industry to do that. They also, the big simulators, even our big industries, unfortunately don't tend to see the value proposition always. I guess partly it's, in our case, our biggest industry being a dairy processing industry. I often joke that milk is our hydrocarbon, but it's not. A hydrocarbon simulator such as HiSys is therefore not entirely appropriate for that process. So there's challenges there, but I think, to summarize, I think a range of tools, and that's what we're talking about as well. To solve different problems, a toolkit I think is really important. So yeah, it could be dashboards I have nothing against. Excuse me, I just need a drink of water.
Yeah, I open another question from, okay, I think that I saw from the chat box from Muhammad Amir Javed. So the question is, what will be the future of this modeling if real-time model are available?
I think real-time models often are available, but I think it's I think actually the Covert tool is a good exemplar for that in some ways, but it's the challenge is always how do you validate those models, and even before that, how do you calibrate those models and then validate them? Yeah, again, it's sort of there is a lot of high powered real-time modeling tools available, but it's how would we best use them? Part of the reason that for the centre that we're involved in is actually to help with, I guess, education. So we're educating 20 PhDs, 15 masters, gosh, it's something like 140 internship students over the course of the program, plus all our undergraduates in the 3 universities that are involved in the program. The idea is that is making sure that they are then expert in to some degree in these tools, and they can therefore apply them. So I think simple answer to a simple question is the future is bright.
The future is bright. That's cool. Yeah. Any other questions, guys, from the participants? Maybe 1 or 2 questions before we end our session for today. You can unmute yourself. You can ask straight away to Prof. Ren if you want to. You don't need to write in the chat box. Anyone?
I would say one thing I might add to this discussion while people are thinking of a question is that education is important in this area. As we were chatting before, Prof. Zainal, I think we're seeing that driven by the students as much as the professors. The students that I'm getting are realizing that they need to be skilled in this area, and so actually it's the future being bright. I think it's actually really good times for potentially for process control, that digital twins and Industry 4.0 is putting a renewed interest in this area and what you can do.
There's 2 questions from the chat box. One is from Fauzi. Is it first principle model sufficient to be considered as a digital twin? First principle model?
Yeah. Well, it depends, as always. We would say, I would ask you, how is it connected to the process? What does it look like? What level of fidelity? So is it steady state? Is it dynamic? And what is the problem you're going to solve? So how does it match that? And I guess, and then finally, what's it look like? Does it have a GUI or that looks like an HMI, or does is a stick figure drawing, or is it 3D CAD? So all these sort of questions you need to ask yourself. Then okay, then maybe it is a digital twin. Maybe it's only a digital model or a digital shadow. Yeah. But good question.
Another question, from Zulfan is slightly out of the box. What is the trick to get the student interested in this area of process control and maths optimization, bro? Wow.
Yeah, that's the perennial question as professors, and I'm sure you, Prof. Zainal, would have an answer for this too. But we have found, and it's a good question. We found that using we suck them in with the idea of real-time simulators and get them sort of playing with the dynamics first before we introduce them to the underpinning modeling and mathematics, and it's so that people kind of learn, almost hands-on learning, that you almost treat even the almost treat them like operators, but you've got the ability then also to educate them about the fundamental principles. So So use a simulator, use a Fauzia's, first principle simulator to simulate a distillation column, and then get them to think about, okay, what's the underlying equations? How do I represent them? How do I actually design a control system? And so forth. So that's the way that we've done it, and it seems to work for us. We have written on the subject a bit, but yeah, it's a constant challenge. I think in my own area of chemical engineering, chemical engineers usually don't go into chemical engineering because they want to become coders or work in Industry 4.0. But they quickly learn that actually they have a lot of the knowledge around the processes that it's very important to those systems. So yeah, it's an interesting one. I think that's getting over that inherent bias that chemical engineering students often have is really, if you can get over that, then you can really enthuse them.
Yep. Maybe last question before we end our session. It's 2 o'clock, 6 past 2 o'clock now. Last question from
now?
Yes.
Can I have one question, please?
Yes, please.
Yes, from Brent. I just want to ask one question to you. What is your opinion based on if you want to use CFD as one of the optimization tool in RTO? Is it possible to combine CFD with process control in real time?
It's a challenge. I guess really when you say CFD, I would say if you think of it more, if you strip it back and think of CFD as more as partial dynamics, partial differential equations that are modeling the fluid mechanics, then and solved by a numerical solver, then yes, it's possible. It's a question of, as always with these sort of applications, is why you would need to do that, and there may be some valid reasons for you to do that. At the moment, the challenge is perhaps twofold. One is the number of people that are capable of actually doing the CFD work themselves. They're a very small subset of people. Increasingly, that's actually it's less specialized as it used to be, but still reasonably specialized. And I guess connecting that to the process, I guess. So fusing those two knowledge areas together, that's the challenge. But yeah, it's feasible, definitely. So you've got to look at it. You'd have to look at it in a use case where you would want to do that. I can think of a couple, but for example, certainly in design and in retrofit, CFD is used extensively in our milk powder industry, for example. But you don't see them used online real time. Good question. And there was another question there as well, I understand, which it's floated by, I missed it. How do I validate the quality of the synthetic data generated? So with particularly that was the example from the geothermal plant. So we were looking at, we're comparing the synthetic data versus the actual data we had from the plant, but also with a validated HYSYS model that we developed of the plant. And what we found was that synthetic data actually sat between, and the n-dimensional system sat between the HYSYS model and the measured data points. So I guess we felt quite chuffed, quite comfortable that we felt the quality of the synthetic data was good, in those points. So it wasn't showing us, it wasn't sort of showing us infeasible or unbelievable results. Remember what we were doing it for? We're really doing it to develop a uniform data set that we can then use for such things as optimization and process control. And so we were very happy with that. We also looked at metrics for those, the quality of those fits, and you saw a couple of those that whipped by in the presentation. But I understand this presentation will be has been recorded and will be available to see later. But we also are in the process of publishing a paper on that work. If you're interested in that, you can contact me.
All right, I think we come to the end of the sessions. Before that, on behalf of the Malaysian Process Control Society, Prof, we are very honored to have you today. We really appreciate your times to be with us in one of the guest speakers in our webinar series 2022. Thank you very much, Prof, for your times. And for the participants, thank you very much for your time as well to be with us today with Prof. And for the participants, we already give you a link for the attendance. So we're going to issue a certificate of attendance for those who are interested. You can log into the Google form and fill up the forms. And apart from that, thank you very much. And thank you very much again, Prof, for your time.